Thank you very much. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. Assalamu alaikum everyone. Today we are going to start an interesting lecture which is related to the bearing capacity of shallow formation. In our previous lecture, we studied about the introduction and different types of shallow and deep foundations. So the foundation types were discussed for the shallow foundation case, and we discussed that the deep foundation or the pile foundation will be discussed in chapter number 4. So an overview was given that how a foundation engineer approached the design of a foundation. Also the foundation selection process, that how we as a geotechnical engineer choose the shallow foundation and deep foundation. So in today's lecture, our main focus would be on the bearing capacity of shallow foundation. Now, what is bearing capacity? What are the terms which are used to define the bearing capacity will be discussed today. Starting with the ultimate bearing capacity, so we will first start with the ultimate bearing capacity, which is Q ultimate. Then whenever the load is applied onto the soil, for example, if you're given with a foundation here is a soil, ground level, load P is applied. This soil will fail in a certain way, so if this is, for example, the boundary of the soil, so whether it's going to fail in such a way that we are going to experience different failure modes. So we will discuss these failure modes in detail today. Okay. So one mode of shear failure is general shear failure. Another one is the local shear failure, and the third one would be the punching shear failure. Then it is necessary to define few terms related to the bearing capacity of the soil. For example, gross pressure intensity, or we can also say that it's Q gross. Please don't confuse yourself with the pressure intensity that is also equal to the bearing capacity of soil. Now, then we will discuss the net bearing capacity, safe bearing capacity, and allowable bearing capacity of the soil. Methods of bearing capacity determination. There are analytical methods, so we will briefly discuss about the bounds methods, the lower bound method and the upper bound method. Then we will move towards the important topic of our today's lecture, which is the Terzaghi's bearing capacity theory and the derivation of the Terzaghi's bearing capacity equation. We will also discuss at the end of today's lecture the effect of water table on the bearing capacity of the soil, that how the water table, if it's changing with depth, or at different location, how the bearing capacity of the soil would change. So it's just an overview that what we are going to get, what we are going to learn in today's lecture. Starting with the ultimate bearing capacity, which is the Q ultimate, it is the least pressure which would cause shear failure of the supporting soil. It is the least pressure which would cause the shear failure of the supporting soil. And we already know that the foundation is designed based upon the two failure criteria. One is the shear failure criteria, and the another one is the settlement failure criteria. So it's the least pressure which would cause the shear failure of the supporting soil. Now, that is the ultimate bearing capacity. Now, what are the different shear failure modes? And in order to understand that, we will go to the board here. So, for example, if we are given with the, let me write that, shear failure. So here is the soil and here is the foundation. Load is applied on top of this foundation. Now when the load is applied, P, the pressure which is exerted onto this foundation would be Q equal to load per unit area. There are different zones which will be created and which will be discussed in detail in Terzaghi's bearing capacity equation derivation there. But for the time being, we will have an elastic zone, and then we will have a radial shear zone, and we will have a plastic zone. So this one is also a third zone. Now, if we are dealing with stiff, let me write here, stiff or dense soils, then we will have settlement, and this is the pressure. So in case of stiff or dense soils, we will experience such type of behavior that the pressure will reach to a point and suddenly we will experience a well-defined failure load. So sudden collapse will occur. In such cases of general shear failure. And that sudden collapse is accompanied with the tilting of footing. Okay. Now, there is another type of shear modes of shear failure. Okay, there is one another thing which we missed here in this case, that we will have a wedge shaped. This is the wedge shaped. There is also this portion is the radial shear zone or the slip surface and also the heaving or bulging of the soil. So all this will happen in the general shear failure mode. Okay. Now, in case of local shear failure mode, we will have a wedge here, which will be created just beneath the foundation, and there will also be a slip surface, and this portion is not prominent, and little bit of heaving will also occur in case of local shear failure. Now, this type of shear failure will occur in high compressibility soils, large settlement would occur, and if you want to draw the pressure versus settlement curve, so it's kind of increasing and increasing when we don't have the well-defined failure load in this case. Okay. Now, in the punching shear failure mode, this is the pressure versus settlement curve here. So in very high compressibility soils, this type of failure mode will occur, and also large settlements would occur in punching shear failure mode as well. And we will only see this wedge type of failure in case of the punching shear failure mode. The details and characteristic of each failure mode is given in section 2.2. So well-defined failure pattern is there, having the wedge slip surface, heaving characteristics, sudden collapse occurs in the dense or stiff soil, and well-defined failure load. Similarly, for the case of the local shear failure and the punching shear failure, characteristics are given in each section. Here we can clearly see the three zones which are produced in case of the general shear failure mode, and two zones are produced in case of the local shear failure mode. Slight heaving can also be seen, and in the punching shear failure mode we will only see the wedge shape, the elastic wedge, which is a rigid wedge attached to the foundation, so it will act as part of the foundation. Punching shear failure mode. This type will occur in dense, stiff soils. This one will occur in case of high compressibility soils, and this one will occur in very high compressibility soils. If you want to draw a figure here for the pressure and settlement, So you can clearly see a well-defined failure load in case of the general shear failure, and now in case of the local shear failure, we cannot estimate the failure load, and that is in case of local shear failure mode. Now in case of the punching shear failure, a reasonable estimate can be made with the failure load, but we can clearly see large settlements are occurring at small pressures. Now we can also draw this, let's suppose, pressure settlement or the load settlement curves for the general shear failure mode, and for the case of local shear failure mode, and for the punching shear failure mode. We can clearly see the pressure intensities which can be achieved based upon the dense or the stiffness of the soil, the compressibility of the soil, and also the lowest can be obtained in case of the punching shear failure mode. Now, a relation or an estimation of the different types of failure mode can also be made comparing with the relative density of the sand. Now, I would request a short discussion. What is relative density of the sand? Who is the seer of the class?
अरे हम क्या पढ़ रहे हैं?
Who is the seer of the class? Who is the seer of the class?
Salman Hamad, sir.
Okay, Salman. So, who asked the question that what we are studying?
सर मैंने पूछी.
Okay, Uzair Khan. So, when did you join the class?
सर मैंने स्टार्ट से ज्वाइन किया, लेकिन सर आपने टेबल्स भी बनाए और वो अभी सिर्फ बताए, लेकिन हम तो समझ नहीं रहे कि आप किस चीज़ की बात कर रहे हैं.
That is the bearing capacity of the soil and the failure modes of the soil. So we are talking and discussing about the bearing capacity of the soil. Now we started with the ultimate bearing capacity of the soil first, that how much the soil can sustain, how much pressure that soil can sustain. For example, if we want to go here, this is the foundation, okay? The load will be applied on top of this foundation. Here we are given with the ground level. So a pressure will be applied on top of this soil. Agree, Uzair? Are you with me? Uzair, can you hear me?
जी सर डिस्कनेक्ट हुआ.
Okay, so now this soil needs to bear the pressure which is exerted onto the soil. Agree? Now, what will be the ultimate bearing capacity or the allowable bearing capacity? Or if generally, if I say as a whole, what would be the bearing capacity of this particular soil? So our main focus, because we are dealing with the shallow foundations in today's lecture, so it will be bearing capacity of shallow foundations. Is it clear now?
बेयरिंग की समझ आती है, लेकिन जो आपने वो डायग्राम्स बनाए उसमें जो लाइंस है और वो
Okay.
zones है, वो क्या है इसका?
Okay. That makes sense. No problem at all. Now these are the different types of zones which are created beneath the foundation. For example, there are different theories that how this soil is gonna behave, okay, and how this failure mode will occur and how the soil will heave when the load is applied. So there are people who are talking about the different failure modes, okay, and as I told you, we will discuss that in great detail in Terzagh's bearing capacity equations when we are deriving it. So the zones are not important, but the main thing is that we will have a failure wedge, the rigid wedge here, the slip surface, this will be created beneath the foundation, and also we will experience this heaving phenomena if the soil is stiff, okay. Then if we are having a highly compressible soil, and if the foundation is placed in that type of soil, then we will experience a wedge here beneath the foundation, and we will experience the slip surface beneath the foundation, and we might see slight heaving or bulging of the soil as well. Then if we move towards the punching shear failure, so the foundation will be punched into the soil, which means we are dealing with a very high compressible soil. So that is what we discussed so far, and I will show you a video here that gives us an idea. I don't know if you can hear the sound of this video, but I will hopefully that will also clarify few things. So to safely transfer the load to the soil, foundation is placed beneath the building, then the compressive and shear forces will occur, and we will experience different modes of failure. It will occur in the loose sands or also in very high compressible soil, and we will have a displacement there, and the failure mode will occur. So we experience very high or large settlements in the punching shear failure. Now, in case of very dense soils, so we will experience these different zones there. Heaving is occurring, as you can see, and tilting is also occurring in case of the general shear failure modes. Different bearing capacity historic failures. This was constructed in Manitoba, Canada. So they underestimated the weight of the grains where they store the wheat grains there and overestimated the bearing capacity of the soil. That's why that structure was failed. Now, what are the different solutions to the bearing capacity failures? So we can change the spread footing with the mat foundation. So the entire footing will add to the stress distribution and which will increase the bearing capacity of the soil. We can also go and reach to the deep strata which is having higher bearing capacity. Pile groups can be used, or we can use different foundation options which are shown in here, like for example grouting, soil mixing, and the compaction as well, which we studied in very good detail in Geotech 1. So is it clear now, Uzair, that what we are studying? Is it clear? Uzair Khan. Okay, thank you very much. Shear, please kindly note down the attendance there. Just see who is not present. At the end of the class, just give me those names of the students who are not present in today's class. Okay, so, and I only need the permanently absent students who comes only for a few minutes or something like that. So just give me those names. I will note down those names here. Let's see. So we reach to the at relative density. Now, Uzair, what is relative
Sir,
density? Uzair Khan, what is relative density? Yes, please.
sir, we have less value of P in case of PSF and greater value of P in case of LSF. Sir, how we are getting less value in case of very high dense soil?
Sorry, let me go to my figure there. So in case of very high compressibility soils, we are having very less bearing capacity, or the failure load is very low. And in the medium stiff soils or high compressibility soils, I would call that we are at the middle portion. And in case of very dense and stiff soils, we are having the maximum value. So what do you think that how it should fall, that the
Sir, okay,
soft
sir, it's
soil should
clear.
give, yeah, so the soft soil is giving us the least value and the highly compressible soil is giving us the middle value, and if you see here the dense and stiff soils are giving us the highest value. So that's what I think so we should experience and what we should get. Okay, Zair Khan, now what is relative density? Any substance divided by the density of the water is relative density. Now in terms of void ratio, if we want to define it, how we are going to define it as a term which is related to the void ratio. So we studied that in geotechnical engineering 1, which was related to the void ratio. Anyone who remembers about the relative density which is related to the void ratio?
It's the ratio of the actual decreasing volume of voids in a sandy soil to the minimum possible decrease in the volume of voids.
Okay, thank you. Anyone else?
Sir, difference of the void ratio of cohesiveless soil and the loosest in the loosest state and the natural state.
Okay, thank you very much. Anyone else? Okay, Osama is saying that this was also asked in the final paper, but we didn't remember. Okay. Actually, when we are dealing with the cohesion-less soils, this is a very important term which is used in geotechnical engineering because it helps a geotechnical engineer to prepare the sample and specifically the cohesionless soil samples. So this is the maximum void ratio which can be related to the minimum density of the soil. And this one is the minimum void ratio which can be related to the maximum density of the soil. And this is the field void ratio. Okay. Anyways, that was just a recap to the Geotech 1 terminologies which we studied. Now we compared the different modes of failures for cohesive soils. Now if we want to find out the comparison with the depth to width of the foundation and also the relative density of the foundation, sorry, soil. So approximately less than 35% of the relative density, the punching shear failure mode will be seen in cohesion-less soils. Now, in between 35 to approximately 70% relative density of the soil, local shear failure mode will be seen. Now, in case of or I would call that as loose sand, and I would call that as medium dense sands and very dense sands. So greater than 70%, we will experience the general shear failure modes. Now that was all about the modes of shear failure. Now we will move towards the pressure intensities or the bearing capacities. For example, if we construct a foundation in the soil, the load is applied so here I would say this is the load or the weight from the superstructure, and here the weight from the foundation, and also the backfill soil, weight of the backfill soil would be exerted here at this depth of the foundation. Now the Q gross would be equal to the weight of the superstructure, weight of the foundation, and weight of the backfill soil divided by the area, and that will be known as the gross pressure intensity. Now, in order to understand the net pressure intensity, please kindly note down that equation because it will be used in solving examples and problems, which can also be used in exams and assignments, quizzes as well. Now, there is another important equation which you can note down, this one. So, if you are asked in exam that please find out the net pressure intensity or the net bearing capacity, so you will first find out the Q gross, which is weight of superstructure, weight of foundation, weight of the backfill soil divided by area, and whatever we get, you will subtract the gamma into D, which is Q, okay, and that is the overburden pressure which is exerted here at the base of the footing. So this is the Q gross. And if you subtract this one, Q, which is gamma into D basically, or we can say Q gross minus gamma into D, this will give us the Q net. Now, if we assume few things, that if the weight of the footing is equal to the backfill soil, which is not in the reality, but if we take the unit weight of the footing and the unit weight of the soil is equal to each other, then we will come up with a simple equation that Q net is equal to weight of the superstructure divided by the area. But as far as the problems examples are concerned, our exam point of view, this equation is more important, that we may ask about the net bearing capacity or the pressure intensity of the soil. Now, what would be the safe bearing capacity? The safe bearing capacity means that if you find out the ultimate bearing capacity, and if you use the factor of safety, for example, the Q ultimate, and we use factor of safety, and this factor of safety can be 2.5 till 3, generally for the shallow foundations. Now, we had a good discussion on why we use the factor of safety. There are several uncertainties due to the loading conditions, sample collection, sample testing, etc. So we will find out the safe bearing capacity. Please kindly note down this equation as well, which will be helpful in exams. Now there is another term, this is the Q safe. Now if you subtract the, for example, Q, this one here. So if we want to find out the Q safe net, so the only thing which you need to do, you need to subtract first the overburden pressure, then this one will give us the Q ultimate net. Now we want to find out the Q safe net, so we need to divide that on the factor of safety, and this one will be safe, but this is the Q safe net. If you want to find out the Q safe, so you can simply take the value from the Q ultimate and divide it by the factor of safety. But if during the exam it is asked that you need to find out the Q safe net, then you need to subtract the overburden pressure which is exerted onto the foundation here, find out the net ultimate pressure intensity, and then divide it by the factor of safety. Now, there are two criteria which we need to satisfy for the design of foundation, and the one criteria says that it is the limiting the settlement, which is basically equal to 25 millimeter, which will be discussed in chapter number 3, or 1 inch settlement. This is the settlement criteria, and the shear failure criteria as well. Now, the allowable pressure is the minimum. Okay, note down that it is the minimum of the Q safe. For example, here, this is the Q safe. So we'll get a value from this one, and we will also, this is the shear failure criteria. Now, there is another criteria, which is the settlement criteria. So we will also get the value of the Q from the settlement criteria, and the minimum of these two will be the Q allowable for that soil and for that foundation as well. I hope it's clear.
Yes, sir. Sir, what did Q gross and Q net tell us?
Q gross is the gross pressure which is applied. For example, how many stories are there? What would be the weight of the foundation? Okay, and the weight of the backfill, and the area on which that pressure is applied. So it is the total or gross pressure which is exerted onto that soil. Now, when you are excavating the soil, so sometimes we are more interested in finding out the net pressure intensity. Sometimes maybe we will not do this backfilling, or even it is very, very loose, so we don't want to consider that in the design. So if this will be the Q gross, okay, it's the weight of superstructure, weight of foundation, and we have the weight of the backfill material divided by area. But if you subtract the gamma into D, this soil and this soil, this will give us the net pressure which is exerted at this level. Okay, so this is the net if we subtract this overburden pressure from the gross pressure intensity. Okay, now there could be different methods which will be used. Now, there is no single method that is 100% accurate in finding the shear strength parameters. Okay, so similarly, there are different methods. Lab tests were performed in finding the shear strength of the soil. Now, we will also be using finding the bearing capacity of the soil, and there will be different types of methods. For example, the analytical methods, which are based upon the Terzaghi's equation, which is our main topic for today's, which we'll discuss at the end of this lecture. Now, Mohr will be discussed in the next class. Hansen equation. There are several correlations that you can correlate the data from the standard penetration test, and which we get the N value here, and from the cone penetration test we get the tip resistance, the sleeve fraction, and we also get the pore water pressure information. But this tip resistance obtained from the cone penetration test is used in finding the bearing capacity of the soil. Now we can also determine the bearing capacity of the soil using the plate load test and the pile load test, and you might have performed the plate load and pile load test, or even gotten the demonstration for the pile load test in Geotech 2 course. There are other methods which are based upon various codes, and the codes provisions will give you an estimate for that particular soil, that what we will get the bearing capacity of that soil. Now, going to the analytical methods, there are different bounds methods. Okay. Now we will start with a very simpler estimation of the bearing capacity, and then we will end up with the Terzaghin's bearing capacity equation, in which we will find out the ultimate bearing capacity of the soil. Now in bounds method, there are two types. One is lower bound and the other one is the upper bound. Now in the lower bound, we will have the true failure load. For example, if there is a soil and we want to find out the lower bound estimate of that soil, now for that, the true failure load will be greater than the upper bound solution. Okay. And in order to do that, very simple approximation was made that phi is equal to 0. Okay. The strip footing was used, and phi is equal to 0. Here is a foundation. Here is the ground surface. Surcharge is applied. This is the Q gamma into D. This is the surcharge or overburden pressure which is applied here. Here is the load of the foundation, and the pressure which is exerted at this particular depth will be Q ultimate, which is load per unit area. Now, lower bound solution says that we need to take two elements. One will be the element number 1, and the second element of the soil would be element number 2. Now, recalling the Mohr-Coulomb failure envelope, okay, this is tau and the sigma. Here is the sigma 3 and here is the sigma 1, and this one would be C cotangent phi. Okay, and this is the sigma d, delta sigma d, we can call that as the deviator stress. Okay, this is the sigma d deviator stress, toric stress. What else? And we also know that sigma 1 is equal to sigma 3 plus delta sigma d. This is the deviator stress, and that is during the shearing stage of the triaxial test. Sigma 1 is equal to sigma 3 at the consolidation stage, and this is the shearing stage. Anyways, that we will take two elements and we will zoom in on these two elements. We will try to find out the stresses which are exerted on these two elements. So for the case of element number 1, sigma 1 will be exerted on the top, okay, and sigma 3 will be exerted laterally. Sigma 1 is the major principal stress, and this plane will be known as the major principal plane. Horizontally, during the plastic equilibrium, for example, if the stress is applied on top of this soil, some stress will be transferred in this direction laterally as well, and that will be exerted on to the element number 2. That sigma 3(1) will be equal to the sigma 1(2), which is exerted on the major principal plane of the element number 2, and this one will be the minor principal plane on which sigma 3 is exerted, and that sigma 3 is equal to Q, which is the overburden pressure here, gamma into D. So for the time being, you can note down that sigma 3(1) is equal to sigma 1(2). Now, if we recall the Mohr-Coulomb failure criteria, so we can write this equation. And as we know that sigma 3(1) is equal to sigma 1(2), which are the lateral stresses applied onto the two elements. As we assumed that phi is equal to 0, and when the phi is equal to 0, this term tangent square 45 will be equal to 1. So we will bring that sigma 3(1) here, and in this case phi is equal to 0, and this whole term will become 1. Then we will bring the 2c here. Sigma 1(1) is equal to sigma 3(1) plus 2c. And as we can see here that sigma 3(2), which is the minor principal stress here, so on the top of this element 2, or the block 2, gamma into D will be applied, and that gamma into D is equal to sigma 3(2). Now for sigma 1(2), which is the lateral stress applied onto the top of on the side of the block 2, so we can also use the Mohr-Coulomb failure criteria, and we can simplify based upon the information which is here, that phi is equal to 0 and this term will be equal to 1. So we will come up with sigma 1(2) is equal to sigma 3(2) plus 2c. Now if we put these equations, sigma 1(2) is equal to sigma 3(2) plus 2c, and sigma 3(2) is equal to gamma into D, so we can write this equation q bar plus 2c. Using the equilibrium condition where sigma 3(1) and sigma 1(2) equal to each other, sigma 1(1) can be written in this form, and the most significant or the important equation for a geotechnical engineer for a lower bound solution will be that Q ultimate is equal to Q bar plus 4C. Now, after solving all these equations, we came up with an equation that gives us the lower bound solution, where this Q bar is the overburden pressure plus that 4C. C is the cohesion of the soil. Now, it is further said that for surface footing, for example, if we place that footing on the surface, the Q ultimate will be equal to, because this term will be equal to 0 at surface, your burden pressure will be equal to 0. And how it's going to be 0? So if we are placing this footing, for example, here, this gamma into D, that is equal to Q. Now, if we make that D equal to 0, which means that we are placing this footing on the surface, this will be for C. So a very rough estimate about the bearing capacity of the soil can be made if we use this equation, that if we only know the cohesion of the soil, this will give us an estimate about the bearing capacity of the soil. So it's just a start. We are going to end on the Terzaghi's bearing capacity equation. Now for the upper bound theorem,
Sir,
the true failure load, if you have any questions, please kindly ask at the end of the lecture. Please hold on to this question. Let me finish the recorded lecture, then we will spend more time on question and answer session. Hopefully your questions will be answered when we explain the Terzaghi's bearing capacity equation. Okay. Now for the upper bound theorem, if we can also make an estimate that there is a true failure load. Now that true failure load will be greater than the solution which we are getting from the lower bound. Sorry, this is the lower bound. So we are trying to estimate the bearing capacity or the failure load. Now this is the upper bound solution. Now in upper bound solution, this will be greater than the true failure load for that particular soil. And for the case of lower bound solution, this true failure load would be greater than the lower bound solution. Now in order to find that, how we can find out, if we place the same footing here and the load is applied and Q ultimate pressure is also applied, here is the width of the footing here. Overburden pressure, which is Q gamma into D, is also applied. And if we have a deformation or displacement of d theta, and here we are given with the sector here, which can be found out from the S is equal to R theta. Delta S is equal to that R, which is the radius, is equal to the width, and this is the theta. These are the external forces which are acting on to the soil, for example, the Q ultimate and the overburden pressure, and this will perform the external work onto the soil, and there will be internal work done by the shear strength of the soil along this slip surface or the failure surface. Okay. This is the undrained shear strength of the soil. Here is the depth of the foundation. Now, if we compare the internal work done and the external work done here, we will come up with the equation which is Q ultimate Q plus 2 pi C. Now we can also write that equation as 6.28 C. If you remember, we obtained for the lower bound solution Q, which is the overburden pressure, and 4C was for the case of lower bound solution. Now in the case of upper bound solution, we are getting Q plus 6.828 C. For the surface footing, this will be equal to 0, and we will come up with the Q ultimate, which is equal to 6.28 C. Now, if you remember, the true failure load due to the lower bound solution here and 6.28 C in the upper bound solution. So it's just giving us an estimate that for phi equal to 0 soil, which is obviously not the real field condition, and the soil conditions are not properly involved here, but it's giving us an estimate that how we can find out the upper bound and lower bound solutions, and how we can find out the ultimate bearing capacity for different soils, or particularly for phi is equal to 0 soils. Now we discussed the limit equilibrium method in slope stability chapter in Geotech 2. Now we can also solve the same problem here using the ultimate load which is applied, overburden pressure which is applied, and the shear strength of the soil, or if we take that shear, the cohesion equal to the shear strength of the soil, because phi is equal to 0, and if we take summation of moments about the O, the central point, if we take the summation of moments and the loads and the stresses which are applied and the moment arms, and we equate this equation, so these are the overburden, the ultimate, and the cohesion of the soil, so we will use the shear strength of the soil, which is equal to the cohesion of the soil here, and if we simplify that equation, again the upper bound solution can be obtained in this manner using the limit equilibrium method. So to Q bar 6.28 C, and for surface footing it would be 6.28 C. And that's how we can approximately and crudely get the upper bound and lower bound solutions. Here we can also see, please note down these equations for the upper bound and the lower bound. We might use these equations for solving the examples and problems. So if you want to take the average of the two, so we can say that it's 6.28 plus 4c divided by 2. So we can get the average ultimate bearing capacity for phi is equal to 0 soil. So that was a very rough estimation for finding the bearing capacity. Now we will move towards the Razaghi's bearing capacity equation, and here we will find out the bearing capacity for C and phi soils. Razaghi's bearing capacity equation is valid for the strip footing, and it is based upon the limit equilibrium method. The depth of the footing should be less than or equal to the depth of the footing, or it should be applied for the shallow foundations. Okay, foundation should be rigid and rough. The soil beneath the footing is homogeneous. Strip foundation with the horizontal base, so the load should be applied vertically, and the surface should also be leveled. Okay, the inclination, the load inclination and the sloping surface will be discussed in the Mohr bearing capacity equation. Okay, so we can say that the level surface and the vertical loads, this Razaghi's bearing capacity is applicable. Another major assumption is the assumption for the general shear mode of the failure. More Coulomb failure criteria should be used for the shear strength of the soil. And as Uzair said that, sir, it's difficult to grasp the concept. The concept there. Now here is a much advanced and detailed explanation given about the failure mode or zones which we draw there. So it's the foundation here. So the load is applied P. This is the width of the footing here. Please confirm that the voice is clear and the screen is visible.
Yes, sir, clear.
Okay, thank you. Now, Razaghi assumed or proposed that there will be a rigid or elastic wedge, this A, B, and J. Okay, let me slightly zoom out. So the first zone, one is elastic, rigid, or even ranking active zone, because the soil is in active state. So that was known as the zone 1. Now please note down that this is the half portion of the failure mode which is shown in this at this page. Okay, now this is the second zone, and here we will have a third zone. So the second zone This angle is phi, which is the friction angle which we got from the direct shear test. The radial zone, this can also be known as the radial zone or the plastic zone or Prandtl zone, and that was named after the work of Prandtl. In fact, the Terzaghi took the work from the Prandtl and he was motivated from the work which was conducted by this researcher, and he named this portion in the honor of the Prandtl researcher. Now, the characteristic of this radial shear zone is that we have a logarithmic spiral here, and this soil is in plastic state and this is in the elastic state. Now, this soil or the soil in this particular zone, and you can see the failure surface is approximately linear. That's why it is known as Rankine passive zone. Now you need to note down here that Terzaghi did not assume the shear strength of, or did not consider the shear strength of this portion of the soil. Rather, he replaced this soil by the surcharge pressure, which is gamma into D. Is it clear till this point? Please stop texting in the chat box. Please stop texting in the chat box. If you have a question, you can note down. Those questions, okay? Please. Now, these are three zones for the Terzaghi's bearing capacity equation. Okay, this is the mechanism or the failure mode which can be seen or which was approximated or suggested or proposed by the Terzaghi. Now, if we take the elastic wedge, this is the elastic wedge just beneath the foundation. The ultimate load which is applied on top of this soil, phi is the friction angle, and the normal force which will be exerted by the soil onto this left side of the wedge here the normal force which will be acted on the right side of the wedge, the weight of the wedge acting downward, cohesion acting on the left side of the wedge, and the cohesion acting on the right side of the wedge. There is passive pressure or passive resistance because the wedge will try to move into this direction downward. There will be a passive resistance from the soil onto that wedge here. Now, this is the angle, friction angle value which we obtained from the direct shear test. The height of this wedge can be found out b by 2 tangent phi. Now the forces which are acting, this is the downward weight will act downward and PP will act upward, but we are having two components of the PP and the vertical component for the cohesion as well. So if we take the summation of forces in vertical direction equal to 0, so this is the Q ultimate into B plus the weight and also the two component of cohesion and the two component of the passive resistance. Now if you want to find out the weight of the wedge, gamma into B and into H. Now that H will be equal to B by 2 tangent phi. So we can write the weight of the wedge here. You can make the correction tangent phi, and we can also name this equation as equation A. Now there is an important point which is discussed here, that PP will have three components. Okay, PP due to the weight of the soil, PP gamma, PP due to the cohesion of the soil, and PP due to or the passive resistance due to the surcharge. Now in order to solve this indeterminate problem, what Terzaghi did, that first he assumed that PP is equal to PP gamma, which in that case PP C will be equal to 0 and PP Q will be equal to 0. Then PP is equal to PPC, which is due to the cohesion of the soil, and PP gamma or the unit weight is equal to 0 and PPQ due to the surcharge equal to 0. For the third case, he assumed that PP is equal to passive resistance due to the surcharge. And in that case, PP, or the passive resistance due to the unit weight, is equal to 0, and PP due to the cohesion is equal to 0. And if we put these equations, we will putting the different PP values in equation A, and after simplifying, we will obtain an equation for the ultimate bearing capacity of the soil, which is CNC plus QNQ plus half gamma B into N gamma. Okay. Now we can clearly see here in this equation that cohesion of the soil is contributing to the bearing capacity of the soil. The surcharge pressure is also contributing to the bearing capacity of the soil, and also the weight of the soil is also contributing to the bearing capacity of the soil. Now, this equation is for the strip footing. Terzaghi further performed model tests were performed, and then the equation for the which was initially proposed for the strip footing was then applicable after proposing different shape factors, for example SC and S gamma. Now this equation can be used when we use different shape factors, for example for round, square and rectangular footing. Please confirm that the voice is clear and the screen is visible.
Yes, sir, clear.
Okay, thank you. Now for SC, for example, for the round footing, you will put SC 1.3 instead of 1. For strip footing, you can use 1 SC and S gamma. These are the shape factors. So based upon those model tests, the experimental test which Terzaghi performed, he introduced these shape factors. Okay, and for the square, SC and S gamma, you will put for these different shapes of the foundations. Now here we are going to do an exercise that, for example, if you want to find out the bearing capacity of the soil, bearing capacity factors and C and Q and N gamma, and NC, NQ and N gamma are dependent upon the friction angle of the soil. So if we want to find out the bearing capacity factors for friction angle 30, please give me the values for NC, NQ and N gamma. For phi is equal to 30. So what would be the value of NC, NQ and N gamma bearing capacity factors for 30-degree friction angle?
Sir, NC will be about 38.
Okay, good. What's your name, please?
Ibrarul Haq.
Ibrarul Haq. Okay, Ibrarul Haq, thank you very much. And this will be counted towards your class participation. And those students who are participating and contributing positively, you already know that you get quizzes and assignments and even the exams there. So when you apply for the rechecking, special concession and special considerations will be given to those students who are positively contributing to the class. So I will remember those names who are positively contributing during the class. So NC, Ibrarul Haq is saying that it's 38. Anyone who disagree with the Ibrar value?
Sir,
Yes, please.
I think it's 28.
It's 38. Okay. Now for NQ,
13.
22.
what will be the value of NQ?
22.
12.
13,
12
sir.
or 12, okay, let me write down. 12, 22,
22.
what else?
13, sir.
13,
23.
23. Okay, so this is 10. Okay, okay, let's go for the N gamma as well. What's the value of N gamma?
10, sir.
10.
20.
20.
10.
10. Anyone else?
19.
19. Okay. Now, for 30-degree, N gamma is close to 20 or 19. Those students will get B grade and these students will get A grade. Now, for the case of NQ, it's like, I guess 20 here, 30 here. So I would say the students who give me the answer with 22 and 23 will get A grade, and these students will get B grade. Now for the NC, so there is consensus on the 38. So let me see if this 30, 40. So if you are giving me 38, I think so that's okay with the 38 value. That's how we make mistakes, and that's how the deductions are applied to your examples and problems there. There are tables also given. Usually the figure is given during the exam to get those bearing capacity factors and to use the equation from Terzaghi's or Mehrhof bearing capacity equation. So that will also be part of in solving the examples and problems in the coming class. Now, if the water table so for example, if the water table is here, and we already know that Q ultimate is equal to CNC plus Q, and I will write and half gamma B and gamma. So if you see here, this is the third term and here is the second term. So the unit weight is used in second term of the Terzaghi's bearing capacity equation. So if the water table is here in the case 1, the second term and the third term both are affected, and affected means that you are going to use the gamma saturated minus gamma of water. So you will use the gamma prime equal to gamma saturated, and you will also use gamma prime is equal to gamma saturated minus gamma of water, because both the term of this bearing capacity equation is affected by the location of the water table. Now in the second case, if the water table is at the footing level or base footing, here this is the case 2. Now in case 2, so we are going to use the gamma is equal to gamma total or gamma bulk here in second term, and gamma prime are the submerged unit weight for the case 2. Now if the water table is below that elastic wedge, in that case gamma will be used as gamma total or gamma bulk for the second term, and gamma total or gamma bulk will be used for the third term as well. In other words, there won't be any effect of the water table because the water table is below the wedge. Now how we will find out the height of the wedge? Slightly modified equation is used here. It's b by 2 tangent 45 plus phi by 2. Okay, so you will need to check the height of the elastic wedge here, and you will use these unit weights in second and third term. Now in the case of case 4, here it will lie in the middle of the 1 and 2, so this is case 4, and if the water table is present in the middle here, that would be case 5. There. Now in each and every case we are going to use the unit weight. For example, in case 4 you can use this equation to find out the unit weight for the second term. Now what are D1 and D2? So D1 D2 are the depths here. So for example, will be the D1, this will be the D2, and this is the depth of the footing in that particular equation. Here we will be given with the ZW, or the height of the water table, and this is the H, which is the height of the elastic wedge, and the equation can be found out using P by 2 tangent 45 plus P by 2. Thank you very much for listening very patiently. Now we will move towards the question and answer session.
सर अटेंडेंस ले लें फिर बाद में.
Okay, we will take the attendance first.